Hi! What I want to talk to you today is about the early universe and its evolution. So you may have heard of the Big Bang Theory, the explosive start to the universe, but have you ever then wondered how did everything evolve from an explosion of hot, dense plasma into these enormous and beautiful galaxies we see surrounding us now? Or in other words, how did we get here? So when I say how did we get here, I don't mean how did humans get here or even really how did the Earth get here. No, what I'm focused on is how we got here. How did we end up on a rocky planet in a rather large galaxy that's just one of billions scattered throughout the universe? To answer that, astronomers have observed deeper and deeper into the universe to gain more insight on how stars and galaxies form and how our cosmos came to be. We can do this because the speed of light is finite. While it's incredibly fast at 300,000 kilometers a second, it still takes time for light to travel astronomical distances, which means that the further out into the universe we look, the longer that light took to reach us, and so the further back in time we see. You probably already know this to some degree, as you may have heard that it takes about 8.5 minutes for the sun's light to reach us, so we see the sun as it was about 8 minutes ago. On cosmic scales, however, light is laughably slow, as it would take 100,000 years for it to cross our own Milky Way galaxy, and billions of years to reach us from the most distant galaxies at the edge of the universe. This leads me to the first concept I want you to know. You may have heard the term light year when studying astronomy, but what that represents is actually the distance that light travels in a year, not time. So light's really fast, meaning that it covers a lot of space quickly, and then after a year it travels one full light year. So just for context, that's about 9.5 trillion kilometers. Neptune, the planet at the edge of our solar system, is about 4 light hours away from the sun, so it takes light 4 hours to go from the sun to Neptune, whereas the nearest star to the sun is about 4.5 light years away. So if you didn't know, space is really, really big. So as we peer deeper into the cosmos, we're peering closer to the beginning of the universe, and we see smaller and smaller galaxies at ever earlier stages of development. So in this diagram, we are at the right, at the present day, 13.8 billion years after the Big Bang. As we look out, we see light from further back in time, closer to time equals 0, as indicated by the top axis. It's also important to remember that we live in an expanding universe, and so as the galaxies of the greater universe expand away from us, their light waves get stretched out and redshifted, appearing more red than they otherwise would. This is the same concept as the Doppler effect, where sirens sound really high pitch coming at you and then really low pitch as they go away from you. Light is also a wave, so if the object emitting the light is moving away from you, its light waves get stretched out and they appear more red. What this means is that we can describe some early era in the universe's history by an equivalent redshift value, and this is shown by the bottom axis here. So on the right, we're at redshift 0, redshift plus 1 gives you 1, and then as you look out, you look towards higher and higher values of redshift where things are more and more redshifted. So just to give you a visualization, if we're here on Earth and we're looking at a distant galaxy, it emits some light, but in the time that it takes that light to reach us, the universe expands and the space between us and it stretches, and that stretches out its light waves, making them redder than they otherwise would appear. So then, over the past few decades, we've been building bigger and better observatories to study exactly how the universe evolved into the one that we see around us today. And currently at the distances we're able to see with the James Webb Space Telescope, we're only finding red blobs of what appear to be some of the first protogalaxies. Their light has taken over 10 billion years to reach us, and astronomers lovingly refer to them as the little red dots. What lies beyond these little red dots, though? Not much, actually. So let's zoom in on that first billion years of the universe, the era that I typically focus on in my research. So on the left we have the Big Bang, which brought the universe as we can physically describe it into being nearly 14 billion years ago. The young universe then expanded and cooled for thousands of years, but because everything was so much smaller and more compacted together, matter and light were actually coupled with one another. And so what that means is photons of light were so energetic and pervasive that they would bounce off of particles more frequently than the particles could find one another and form an atom. So at first, the universe consisted of nothing but hot plasma. Then about 400,000 years in, we have an event called recombination and the release of the cosmic microwave background, or the CMB. So at this point, the universe had expanded enough to allow the first stable atoms to form, and then the photons of light that were bouncing off of them and keeping them from forming then streamed off into the greater universe. So this decoupled matter from light in basically the blink of an eye. So before recombination, we have hot plasma, particles, and radiation, and then after recombination, the particles cooled and condensed, recombining into atoms, and suddenly we have a dark universe filled with gas. And so, as a refresher, hydrogen is the lightest element in the periodic table. It's also the most common element in the universe by far. It consists of just one positively charged proton and a negatively charged electron bound to it. Prior to recombination, though, electrons and protons couldn't bind together because photons of light were so energetic and pervasive that they would rip the electrons off of any protons as soon as they found each other. So again, before the CMB, we have hot plasma. After the CMB, we have neutral gas, and light is free to travel across the universe. So we now see this light from this decoupling event as the CMB, which looks like this. And it's the oldest light that we can ever hope to detect in the universe, just a few 100,000 years after the Big Bang. So basically what you're seeing here is the flash of light that was released when the plasma of the universe suddenly cooled and condensed into a gas. After recombination then, the universe was a much calmer place, now filled with neutral hydrogen and a bit of helium gas, as well as the CMB radiation. But it's otherwise dark and frankly kind of boring, so we refer to this era as the cosmic dark ages before the first stars and galaxies ever formed. Now another key concept here is that when the universe was very young, there was pretty much only hydrogen and helium everywhere in the entire universe. Astronomers then lovingly refer to every other element as metals. So oxygen, carbon, nitrogen, all of those are considered metals, and all of them are non-existent at this time. Then after a few tens of millions of years or so, the first stars would form and then begin lighting up the universe again. So the radiation that was emitted by these first stars then began to ionize the hydrogen and helium atoms that littered the universe. So basically, a photon of light from an early star would hit one of these atoms of hydrogen and helium and rip the electrons off of them, which, if you recall, was what exactly was happening before recombination. With the continuous rise of the first stars and galaxies and their radiation output, this ultimately led to a full reionization of the cosmos, where every hydrogen and helium atom loses their electrons. This is referred to as the epoch of reionization, which ended about 12 billion years ago. And so to recap, immediately following the Big Bang, all matter is hot ionized plasma. Then after the CMB was released, the universe was filled with neutral gas, which was then slowly reionized by the first stars and galaxies, meaning that most of the universe nowadays is once again an ionized plasma, just now with stars and planets and galaxies littered throughout it as well. So now let's revisit my original question of how did we get here? So here we have the CMB, and you can clearly see a lot of structures in this image. However, the fluctuations you're seeing are actually really, really small. From the deepest red to the deepest blue on the map, the temperature only fluctuates by 1/100,000th of a degree. That is remarkably smooth. So much so that we actually had to revisit our theories to explain how the Big Bang resulted in a universe where one end was exactly the same temperature as the other side of the universe. So just take a moment to think about that. Everywhere and everything is the same temperature. Everything in all directions is made of the same material. It's the same gas, the same temperature, the same density. So then the question then arises, how does this smooth, almost perfectly uniformly distributed universe evolve into the galactic superclusters and cosmic voids we see in the modern universe? How do we evolve from near uniformity to a universe filled with voids that are orders of magnitude less dense than the galaxies and filaments that are strung between them? To answer that, astronomers are studying this transition period from the cosmic dark ages to reionization, an era known as cosmic dawn. The problem with this era, though, is that it's surprisingly hard to observe. So you may be wondering how that's possible, since we are aware of the CMB and it's much further away. But that's a result of the expanding universe and cosmic redshift. So if we point our telescopes at nearby galaxies, we see them emitting light all across the electromagnetic spectrum. So all electromagnetic radiation, or light, falls somewhere on the spectrum. So astronomers will use light and radiation interchangeably. So whenever I say radiation from the first galaxies, I'm referring to the light that they emit. So this spectrum ranges from very low energy radio waves with very long wavelengths to the very energetic gamma radiation with very short wavelengths. In the middle then is the band of visible light that we're able to pick up with our eyes, and that makes up less than 1% of the whole spectrum. So as we look at nearby galaxies, we can see ultraviolet light from their star formation, X-rays from their black holes, and infrared from their gas and nebulae, and then everything in between. On the other end of the spectrum, the CMB shines in the microwave and the radio bands and is coming from literally every direction on the sky, so it's relatively easy to pick out and observe. During cosmic dawn, however, the first galaxies are relatively small, faint, and mostly observable in the infrared due to that cosmic redshifting. This complicates things because a lot of astronomical objects appear to us in the infrared. So when we find a very redshifted galaxy, the trick is to determine if it's redshifted due to cosmic expansion and it really is that far away, or if it's redshifted, say, due to gas and dust that's just in between us and it. So to sum up so far, we have this transition period in the early universe that sees the cosmos evolve from a cold, dark gas to galaxies and clusters reionizing the universe. Our current observations are just beginning to scratch the surface of this era, and so to predict and interpret the results for current and future observations, we need to simulate the rise of the first stars and galaxies, which is what I do with my research. So now that we have the big picture cosmological context, let's dive into how we actually study this epoch of the universe's history. So the first generation of stars to have ever formed is known as population 3 or POP3 stars. So you may be wondering then, why 3? Why not 1 and 2? Well, POP1 stars are stars like the sun, modern day stars with metals, remembering that everything heavier than helium is considered a metal. POP2 stars were then discovered later as we found this population of old, relatively low metallicity stars that are scattered around the outskirts of the Milky Way. POP3 stars then arose as the theoretical first generation of stars, ones with no metals whatsoever, meaning that they were made purely of hydrogen and helium. Since they were the third group described by astronomers, they are named POP3, and so the more you learn about astronomy, the more you realize that we are terrible at naming things. Anyway, from the Dark Ages arose these first POP3 stars, which would live out their lives, fusing elements in their cores into heavier metals, and then they'd eventually die, exploding into supernovae, and then enriching the universe with their metals. This would ultimately lead to POP2 stars, and then billions of years of enrichment later leads to our modern metal-enriched population 1 stars, like the sun. Now, a key concept for star formation is that to get from a massive cloud and gas in space to a burning luminous star, the cloud first needs to cool down. So you may be wondering, why does it need to be cold to form something as hot as the sun? Well, this is the age-old battle between radiation pressure and gravity. So a cloud of gas in space consists of atoms, obviously, but they also have radiation then bouncing around the cloud between the atoms. So photons of light will scatter from atom to atom within the cloud and impose a bit of energy on the atoms when they do. The large-scale result of this bouncing around is a radiation pressure that kind of puffs up the cloud and heats it up, supporting it against gravity taking over and collapsing it in on itself. So in order to get this big diffuse cloud into a hot dense star, we first need to radiate away that energy and cool it down. As the gas cloud cools, gravity actually begins to win over the radiation pressure and the gas begins to collapse in on itself. And eventually the center of the cloud reaches a high enough density that the atoms start to fuse together. So the proton of a hydrogen atom can get packed so tightly with other atoms that the protons will actually collide and fuse into one atomic nucleus. And this is how heavier elements and metals are made, by the continuous and relentless nuclear fusion that's happening within the cores of all stars. So this nuclear fusion then emits a tremendous amount of energy in the form of radiation because it's basically the opposite process of atomic bombs ripping nuclei apart. So this explosive release of atomic energy then pushes back out against the collapsing cloud and prevents more gas from falling in on top of it. Eventually then, a balance is reached where gravity is pulling in with some force and radiation pressure from the core is pushing out with the same force. It's at that point then we say that the star is born, and it'll continue this balance for a few million or even billions of years. Now, POP3 stars have no metals, and that's very important because it turns out that heavier elements are actually better at radiating away heat. So without any of these metals, the gas cloud cannot cool as efficiently, meaning that it takes a much larger gas cloud to have gravity win over that cooling. So for enriched stars like our sun, the cloud would cool so quickly that it would break up and fragment into smaller clouds, resulting in a cluster of small metal-enriched stars. For POP3 stars, though, there's far less of this fragmentation, meaning that we expect the first stars to be far more massive than modern-day stars. So a common unit of mass we use in astronomy is the solar mass. The mass of our sun is about 2 × 10⁻30 kilograms, or about 2 followed by 30 zeros. That's one solar mass given by that M circle. And a POP3 star is expected to be hundreds of solar masses on average, possibly even thousands of times our sun's mass. So now that we know the basics of star formation, we can extrapolate this to galaxy formation. A bunch of POP3 stars form in the same region, and we have ourselves a protogalaxy. But again, how did we get here? Recall that after recombination, we saw a universe that was almost perfectly smooth. Almost. Tiny fluctuations in the density and temperature would therefore correspond to tiny differences in gravity and radiation pressure. So slightly overdense regions would have a little bit more gravity than their surroundings, meaning they could start to pull in a little bit more matter. That makes their gravity stronger, and it keeps pulling in more, getting more gravity until the first stars and galaxies form within those regions. Slightly underdense regions would have the opposite effect, where they would start to lose their matter to their surrounding overdense regions, leading to these enormous cosmic voids with very little matter star formation. So if we could see the CMB as it was today, the red bits would be galaxy clusters, and the blue cool bits would now be voids. And it's at this point then I'll finally bring up dark matter. So you may have heard of dark matter while listening to things about astronomy. Essentially, as we look at the motion of galaxies on very large scales, it appears that there should be more gravity and therefore more matter permeating the universe to explain their behavior. Since we cannot see any of this matter with our observations, we dub it as dark matter, and astronomers are tirelessly working to figure out what it could possibly be made of. The reason I bring up dark matter, though, is because it's currently believed that most, if not all, large galaxies reside in what's known as a dark matter halo. So there's this unseen large blob of matter that's surrounding galaxies, just like our Milky Way here, that we cannot see. But this model, including this halo around the galaxy, more accurately explains the motion of the stars within our galaxy and the motion of our galaxy throughout the universe. So we need to include these in our simulations. For the first stars and galaxies forming, simulations then become much more expensive once we get into cosmic dawn, because we go from having gas and gravity to having stars and radiation, supernovae, feedback, all of these things that now need to be accounted for. So this leads me to the core issue that I face with my research, something that I've dubbed as the scale problem. Basically, if we want an early universe simulation to be as accurate as possible, we have to account for as much astrophysics as possible. The problem with that is that a lot of the important astrophysical processes span a very wide range of distance scales. So on the scale of a few light years, we have the gas that's cooling and collapsing to form stars. These stars can then explode and enrich the surrounding hundreds of light years with their heavier elements, while the dark matter halo itself is on the scale of a few thousand light years. On very large scale, there are fluctuations in the bulk motion of gas, basically winds that make it really hard for gravity and the halos to bring in that gas, cool it, condense it, and collapse it into the first stars. And then finally, on the largest scales, it turns out that the radiation from the first galaxies is actually able to reach hundreds of millions of light years out into intergalactic space. And it can heat up and irradiate other regions of the universe and make it harder for those regions to cool and form stars of their own. So the scale problem says that if you want to have an accurate simulation of cosmic dawn, you have to include all the relevant astrophysics across all these scales. But doing so is computationally prohibitive and just simply impossible with our current techniques and technology. So what do? How do astronomers overcome such a problem and build simulations of the first stars? Well, it all boils down to simplifying assumptions. We clearly don't have the power to simulate every particle interaction in the universe to study the evolution of the cosmos, so researchers will make some simplifying assumptions that make the calculations easier. Though exactly how simple you're making your simulation is a matter of what you're trying to study. So just to give you a sense of the types of simulations that astrophysicists use, we can look at the two most extreme kinds. So all simulations attempt to either predict or verify observations with telescopes. So theoretical models and observations go back and forth. Simulations tell observers what to look for and expect, and then when observational data comes in, they can use those, the theorists can use those to refine their simulations and give better results, more accurate understanding in this nice, helpful feedback loop of science. So the most simplified simulations are known as analytic models. Basically, these will make some universal assumptions about star formation and feedback, and then use a bunch of equations to get an average result. So instead of simulating a cloud collapsing collapsing into a star and then following the resulting radiation from that star, you can just assume that stars are forming at some constant rate throughout the volume without actually resolving them. So then you can very quickly calculate the intensity of the radiation that's coming from that and get some observable estimates. These simulations are great then for probing different ideas and theories, as you can very quickly change your assumptions to see how the results change to get an idea for the overall behavior you expect. So we can turn the knobs to increase star formation or the feedback intensity and see how the predicted observations would change with that. Then, when we get better observational data, we can narrow down what parameters were actually giving us those results and then refine from there. Unfortunately, though, due to their simple assumptions, these models are very limited in their accuracy and can only be used to get average general trends. So, for example, I took this from a first paper I published. All you need to know as the y-axis is the amount of star formation, and time is going to the right. So I'm showing pop 3 star formation in orange and pop 2 in blue. And what I'm doing in each of these panels is just turning the knobs on one of my parameters. So how quickly the first stars are forming, how quickly they enrich the universe, how energetic their supernovae are. So if I turn these knobs, the results change a little bit here and there. And then this gives us a range of results that we expect. Given better data then, given observational data, we can decide on which of these parameter combinations is the best and most reflects reality, and then refine from there. On the other extreme, we have hydrodynamic simulations, or hydrosims. These are highly complex simulations that try to include as much astrophysics as possible, and then in doing so, they are limited to relatively small volumes. So we can now resolve this cloud of gas and follow its gravitational collapse down to forming a star, determine its radiation output using our most accurate theories. But then the problem with these is that you can't simulate a very large cosmological volume with hundreds or thousands of galaxies, because then that becomes computationally prohibitive again. So these take a very long time to run, with the biggest and baddest simulations taking several months to run one iteration on a supercomputer. So that means you have a very limited range of knobs to turn, because each iteration is going to take another few months and a lot of funding to run. So while analytic models can run quickly with varying assumptions, hydrosims are slow but far more detailed and accurate. So here's just an animation of a hydrodynamic sim. Basically, they'll just populate a volume with some gas, given some fluctuations in density here and there, and then just let it evolve under gravity. So gravity takes over, they let things fall together, collapse into forming the first stars, emitting radiation out, and you can see a lot of these structures forming on here. So it should be clear that there is a lot more information in these hydrosims than there is in these analytic sims, but again, it all depends what you're trying to study, because you only get one shot at the hydrosims, a few maybe, and you have as many as you want with the analytic choices. So my work then falls somewhere in between these two types of models, something known as semi-analytic or semi-numeric simulations. These are a step above the analytic models because they include some more complex physics on top of their basic assumptions, but they're not as complex as the hydrosims, since we're still trying to simulate a very large volume. So what I'm showing here is the underlying density field and the bulk motion of that gas that I mentioned earlier. So each pixel here is millions of light years across, as you can see by the scale bar at the bottom. And so from the density field, we can see that some regions are more or less dense than the average. And we can also see some regions that have more strong winds that'll make it hard for gravity to collapse and form the first stars. So each pixel here represents something like our local galaxy group surrounding the Milky Way. And I filled each one of them with a simple analytic star formation model. So each of these cells can then form stars based on its own density, wind speed, and radiation, and then I can calculate the resulting radiation from that at each step along the way. So let's take a look at the results. Here I'm showing you a slice through the middle of my simulation volume. On the left is the radiation feedback, and then the middle is the POP3 stellar mass, and then on the right is the POP2 stellar mass. So initially we see radiation pouring out from the very first stars in this box, which are not in this slice, so we just see their light, until eventually we see POP3 stars forming within this slice, and then after enough time for them to live, die, and enrich their surroundings with metals, we see POP2 stars forming as well. And then if I put up the underlying density field and the wind speed, we can actually start to see some of these structures forming in a similar shape. So you can see very high wind speed regions, like on the bottom right here, have far less star formation than other regions. More overdense little pixels will have more star formation than pixels that have far less density. So this all will give me a more accurate result than an analytic calculation and more flexibility to adjust the parameters than what we get with hydrodynamic sims. But what is this all for? If I can't easily observe the first stars and galaxies, what am I trying to simulate? The answer to that is known as the cosmological 21 centimeter signal. Very exciting name, right? Well, it's one of the most important and sought after observations in modern cosmology, so let's talk about it. So what is the 21 centimeter signal? Well, it arises from atoms of hydrogen, which we have talked about earlier. So here we have a little red sphere, that's the proton, and we have our little gray electron orbiting around it. Now, crucially, both of these particles have a quantum spin that can either be aligned with each other or anti-aligned with each other. So in the top half where it says F equals 1, the spins of the proton and the electron are aligned with each other. That means that the electron's in a slightly higher energy state than it otherwise could be, and since electrons are lazy and want to be in the lowest energy state possible, this spin alignment can't last forever. Eventually, the electron will spontaneously undergo a spin flip transition. The spins become anti-aligned, and the electron falls to the slightly lower energy F equals 0 state. This transition then releases a single photon of light with a wavelength of about 21 centimeters, hence the name. Interestingly though, this transition is actually forbidden by the laws of quantum mechanics, so it's actually very rare and only occurs about once every 11 million years on average. So if you were to somehow obtain a single hydrogen atom in this F equals 1 state and keep it in like a sealed jar on your shelf, it would take 11 million years on average for that electron to undergo the spin flip transition. Lucky for us though, about 3/4 of all the matter in the universe that's not dark matter is made of hydrogen. So no matter how rare this transition is, we still expect to observe a clear 21 centimeter signal from the early universe where everything was neutral hydrogen gas. What makes this signal so important then is the fact that it only comes from your standard hydrogen atom. So as cosmic dawn proceeds and more stars and galaxies form, their radiation starts to ionize more and more of the hydrogen atoms littering the universe until it's all eventually ionized. So if a hydrogen atom becomes ionized, its electron's been ripped off by light, meaning it has no electron that can undergo that spin flip transition. That means if we can observe the 21 centimeter signal at different times in the universe's history, that would tell us how much of the universe was ionized at those times. And since the ionization of hydrogen depends on how many stars are forming, then the 21 centimeter signal can actually trace how quickly and intensely the first stars and galaxies came to be. So how do we observe the 21 centimeter signal? We typically describe its strength in terms of its differential brightness temperature, this delta TB. But what does that actually mean? To answer that, imagine we're observing the CMB here on Earth. Now, space may be rather sparse, but it's not empty. Pervading the billions of light years between us and the CMB is all that intergalactic gas that was formed during the Big Bang. This gas in the intergalactic medium will have some temperature that we can just call TIGM, and that means that the atoms in it and this gas cloud are vibrating and colliding and sending photons scattering off one another. This can actually excite the electrons in hydrogen atoms and lead to the emission of a 21 centimeter photon. So we actually quantify the amount of hydrogen in this excited state as the spin temperature. So while it's also a temperature for the intergalactic medium gas, it's specifically worried about the hydrogen atoms that can emit 21 centimeter. So it's different from the IgM temperature as you would think of it. It's kind of like if we were to take the temperature of this room, that would be the IgM temperature. And then if we were to somehow take the temperature of just the oxygen atoms in this room, not the nitrogen, carbon dioxide, or whatever else, that would give you the spin temperature. And so what we do when we observe the 21 centimeter is we observe the differential between this temperature and the CMB backlight temperature. So the difference of these two temperatures, we take the difference, multiply by some math to account for redshifting and such. And essentially, if the CMB temperature is higher than the spin temperature at a given time, then the 21 centimeters temperature will be negative, and we'll see the signal in what is known as absorption against the CMB. So basically just imagine a cloud of just a regular cloud blocking out the sun. So the light of the sun is largely absorbed by the cloud, but you can still kind of see the ring of the sun just dimmer than you would expect otherwise. Same thing's happening here, except the sun is the CMB and the cloud is a cloud of intergalactic gas. Alternatively then, if the 21 centimeter signal is, or if the IgM spin temperature is higher than the CMB, we'll see an emission against the CMB. To kind of keep the same analogy, it would be as if that cloud of gas that's blocking out the sun is somehow so hot that it's actually glowing. So the glow of that cloud is adding to the sunlight that's coming through it, and we see it as hotter than we expect. So the main point of this is that the 21 centimeter signal strongly depends on the amount of hydrogen that's pervading the cosmos at a given time, as well as its temperature. And as we learned from the beginning of this talk, there's an era of the universe that is completely filled with neutral hydrogen atoms. So if we can map out the fluctuations in this 21 centimeter signal across time and space, that would be revolutionary to our understanding of cosmic dawn, as it would help us constrain the rate and intensity with which the first stars and galaxies came to be. So here is a diagram of the predicted 21 centimeter signal across cosmic history. On top is a visual of what the 21 centimeter intensity would look like, where blue colors are cooler than the CMB and red is warmer. Notice that the difference in temperature is in millikelvin, so the difference that we're measuring is actually quite small. The bottom then is the average 21 centimeter brightness temperature over time, with the dashed line at 0 representing the CMB. So just like before, time evolves to the right with time since the Big Bang on the top axis and cosmic redshift on the bottom. But now we're just looking at this transition period from the dark ages to the end of the EOR, because that's where the amount of hydrogen atoms is changing the most, and therefore is the best for using 21 centimeter to study it. So initially in the dark ages, we just have gas everywhere, no stars, no radiation, other than the CMB, which is hotter than the gas. So we see the 21 centimeter signal in absorption. At first, it seems that the gas and the CMB temperature are kind of approaching the same temperature. Then the first stars and galaxies begin to form. Now, when this first starts happening, they actually began to cool down the gas for a short time due to some wild physics known as the Wouteisen field effect. But I'm going to spare you all the details of that, so just know that this sudden drop in the 21 centimeter brightness is a key prediction for cosmic dawn. After some time then, enough stars and galaxies will have formed such that their radiation begins to properly heat up the IgM gas, and eventually they heat it up to above the CMB temperature, and we have this transition from absorption to emission. From then on, the continuous radiation from these galaxies will ionize ever more of the hydrogen gas in the universe, and it will cause the signal to grow weaker and weaker with time until the IgM is completely ionized and the signal disappears forever. So you can think of the early universe in 4 separate eras. The first with no stars and neutral gas everywhere. Then the first stars form, and their weak radiation actually cools the gas down. With more and more radiation and stars, we have the heating up of the gas, and then eventually it's so much radiation that it begins to ionize all the hydrogen. So the most least well-constrained and most exciting era then to study is cosmic dawn. So simulations of cosmic dawn are very popular in astrophysics right now because they're being used to study how we got here. But a lot of these simulations, as we have seen before, have to contend with the scale problem. My work, on the other hand, has effectively solved the scale problem, meaning that we can simulate star formation and then translate that resulting star formation history into accurate predictions for the 21 centimeter brightness temperature. Now, to do this, we have to account for a lot of key processes, and this requires quite a bit of math, which I have coded up into a simulation. So let's see how the results look. So again, what I'm showing here are central slices of the volume. On the top, we have the cumulative POP2 and POP3 stellar mass alongside the radiation intensity. In the middle is that IGM spin temperature and the 21 centimeter signal. Then on the bottom is the average temperatures with the red line indicating the current time. So we start to see radiation pouring out from the first sources, irradiating the volume from early on, and we eventually start to see star formation within this slice. And we see during this time the 21 centimeter signal is approaching 0. Eventually the radiation from these first galaxies becomes intense enough to drive this initial cooling phase, and the whole volume starts to drop in temperature. So this gives us what's known as that absorption trough before significant radiation builds up and then starts to heat everything back up again. So we never quite reach a positive brightness temperature before the end of my simulation, but we still get this characteristic dip. So what's next? Well, we can easily then turn the knobs on our simulation to see how the resulting 21 centimeter signal changes thanks to the semi-analytic nature of the simulation. Then, when observations of the 21 centimeter signal are taken, we can compare that data with our simulation results and then adjust accordingly. It's also then helpful to compare with other contemporary simulations, like I'm doing here, to see how different assumptions and techniques other researchers use impact their results. So then with observational data, you can further narrow down the impact of individual parameters on the final result and get a better simulation from there. However, we have very little observations to go off of. In 2018, the EDGES collaboration published their supposed detection of the 21 centimeter absorption trough. However, this finding is quite controversial since it is far deeper than anything simulations had predicted yet. Most researchers believe that there's something incorrect here because it would require some substantial changes to our understanding of cosmic dawn, but we have to wait for more observational data to come in to either verify or refute this EDGES data. So here I'm showing you the EDGES data with this dashed line compared to a bunch of my simulation results, which are the solid colored lines up at the top. So you can see how deep this absorption trough is. Looking to the future, however, there are several planned experiments expected to come online to help with this observational task. Two key observatories are actually right here in South Africa in the Karoo Desert. These are Hera and SCA, the Hydrogen Epoch of Reionization Array and the Square Kilometer Array. They're both still in the process of coming online, but preliminary data is being taken with both of them. And then once we get some robust, unambiguous detections of the 21 centimeter signal then, it will be immensely helpful in then refining our simulations and theories for cosmic evolution in the early universe. It might now seem that we have a pretty good idea of what to expect for our cosmic dawn observations, but there is actually quite a bit of uncertainty left. One key aspect that we can hope to learn about is the mass distribution of the first stars. POP3 stars are expected to be more massive than modern stars, but exactly how much more massive is still an open question. Are they all hundreds of solar masses? Can they reach thousands, tens of thousands? Or can you have a POP3 star that's the same mass as our sun? We don't know. Different stellar masses will have different properties and they'll affect the universe in different ways. This leads to another possible exotic physics like POP3 supernovae. So when a modern star undergoes a supernova, the radiation pressure inside of them can no longer support itself from the gravity pushing in. So radiation pressure fails, gravity wins, everything starts falling towards the core. The entire mass of the star slams into the core, igniting a thermonuclear explosion that then blows it all back out. And that's what a supernova is, and it leaves behind either a white dwarf or a black hole. POP3 stars could be so massive that they actually have exotic supernovae that result from things like antimatter building up in their cores or general relativistic gravitational effects that completely blow the star apart and leave nothing behind. These would be way more powerful supernovae than ones we have in the modern universe, and so they could very well affect the hydrogen abundance and therefore the 21 centimeter signal during cosmic dawn. There's also other exotic possible first sources that could have existed in the universe besides your standard stars and galaxies. It's possible that supermassive stars could have existed with tens of thousands of times the mass of our sun, or even black hole quasi-stars that are so massive that their cores already collapse into a black hole, but the explosion wasn't enough to rip the star apart. So we have a star bigger than our solar system, powered by a black hole at its center. Such extreme and exotic objects could have only existed in the early universe, and they would obviously affect their surroundings and potentially alter the 21 centimeter signal. There's also the possible existence of primordial black holes, which could have formed right after the Big Bang, meaning that the universe could be littered with tiny black holes gobbling up matter and emitting radiation that could have some effect on the 21 centimeter signal. Another key mystery in astrophysics is the origin of supermassive black holes. It's currently believed that most, if not all, large galaxies contain some supermassive black hole in their center with masses of millions or even billions of times that of our sun. The problem with that, though, is that our current understanding of cosmic evolution doesn't allow for enough time since the Big Bang for them to grow to the masses that we see them as now. Supermassive POP3 stars could be a potential answer to this because they could have given us some very massive black holes in the early universe, but we need that observational data to back up such claims. And finally, these observations could also help us nail down the nature of dark matter. As I said before, we expect there to be quite a bit of unseen matter littering the cosmos to explain the observed behavior of galaxies on large scales, but what that dark matter is made of and how it interacts with normal matter is still up for debate. So these aspects of dark matter could then affect how gravity pulls together the first structures and how halos form and thus affect cosmic dawn. So there are dozens of theories that modify our current understanding of dark matter to attempt to explain some current observations, but none of them have yet managed to fully explain the universe, and so the search continues. And so with that, I will leave you with some main takeaways from the talk and a special thank you message.